So just a few more topics I wanted to cover to finish this, and this was a question which was asked in one of the earlier lectures, and it's about power management modes in the chips, and this is there in the textbook. Also, you can see a discussion on this. Basically, now modern chips have all this power management features, and this is an example from the Intel Atom, which is a chip designed for mobile platforms. So it has a number of low power features. So this is the high frequency mode, CO high frequency mode. So where they have, so these are the various states, the power states. It can be C0 HFM, C0 LFM, which is low frequency mode, then C1, C2, C4, C6, and this is explaining what are all the things that is happening. In the high frequency mode, you have the highest voltage to the core, which is 1 volt. The clock frequency is the highest. The PLL is generating a clock at 2 gigahertz. All the caches are being used fully, and it's active. Okay, and it has the highest power of about 2 watts. Typically, for mobile phones and so on, the power, that is kind of the power budget. You want to have a couple of watts budget, not more than 2 watts. Desktops could go up to 10 watts. Maybe laptops, desktops could be a little bit higher. Servers, high-end servers which are kept in data center could be about 100 watts. Right, so that is kind of the. So now they have a mode where it goes into a low frequency mode. In this low frequency mode, what they do is they reduce the clock to 600 megahertz. Either it runs at 1 gigahertz or 600 megahertz. Just these two frequencies are there. And as we had discussed in the last few classes, when you reduce the frequency, you can reduce the voltage also. Right? So that's what they do. They also reduce the voltage to 0.75 volts. They go and program the voltage regulator to go and generate the lower voltage. So the power consumption comes down. Now they have not given what the power number is for this. So what is your guess, the power number? How would you calculate the power number? Right. So the first guess would be, let us say all the power is dynamic power. In case of dynamic power, power is proportional to frequency and voltage square. Capacitance will remain the same between the two states. Nothing has changed. So what you do is you say, okay, my frequency has gone from 2 gigahertz to 0.6. Maybe factor of 3 it has reduced. Voltage has gone from 1 to 0.75. So voltage square has gone from 1 to about maybe 5. So half. Right. So V square has reduced by half. Frequency has reduced by a third. So you can say dynamic power will reduce by a factor of 6. So if everything was dynamic power, power will come down to 1/6 of 2 watts. Okay. But you don't just have dynamic power, you also have static power. So now what is the static power it could be consuming? Well, they have not given any information, so it's very hard to say. Okay, but you can kind of make a guess. As we said, typically in these processors, the power consumption is about a third for the static, 2/3 for the dynamic. It's just a rough thumb rule. Maybe it is 20%, 80%. I mean, we cannot we cannot be 100% sure what the number is, but it's somewhere between 20 to 30%. Based on that, one thing you can say is maybe the static power doesn't change. Okay, you say because it's independent of frequency. So the same, if it was 20% of 2 watts, that is 400 millivolts. Here also it's 400 milliwatts. Okay, so that is the next level of estimation. But then you say that the voltage has also reduced. From 1 it has come to 0.75. So now static power is I leak times V. Now you say, okay, let me assume I leak doesn't depend on voltage. So then you can scale the static power from 400 milliwatts to 0.75 or 400 milliwatts. And dynamic power will be the remaining 2 watts minus 400 milliwatts is the dynamic power, which scales by a factor of 6. You put the two together, you get the estimate for the power. Now I leak depending on voltage. How do you estimate that? That really depends on the dibble and all that. So now you need more information about the process, at which point, it may not be worth going into that level of accuracy, because anyway you want a higher level, just an estimate for what the power is. So what we get here is, what do we get? The power reduces from 2 watts to about 280, 1600, about 500 to 600 milliwatts. That's where it comes down to. Oops. Then they have higher power state, further power down state, where what they do is they have the PLL running, but they shut off the core clock. That means no computing is happening in the chip. But data is there in the L2 cache. The caches are memories which are storing temporary information, which allows fast access and processing. Information is there in the main memory, which is outside the chip, but inside the chip there are specific memories called caches which hold the information for quick access and computing. So the L1 is the cache, the memory closest to the processor. L2 is a little bit farther away. So L1 is flushed. That means they have removed all the information from the L1, and in fact they shut down the power to L1. That is why it's all lost. From there, when you want to wake up, because now it has gone into this kind of inactive mode, it takes some amount of time. They say less than 1 microsecond, and there is some amount of power. Power is less than before because things are now off. Things are not, there is no clock, and they have cut down the power. Then what they do is they can have another power down state where half the L2 cache is flushed. So the size of the L2 cache is reduced by half. How do they do it? Probably the L2 cache itself had two pieces. One piece they just disconnect the power through maybe power gating and removing the clock. When you do that, you reduce the leakage of that. So you reduce the power even more. Of course, it takes more time to get out and wake up, because now even less information is there inside the chip. Everything is there in the main memory. So you have to first restore it, then you can start your work. So that is why it takes longer time. And this is the deepest sleep state where everything is off. There is no information in the chip. Okay, you just have a PLL. Even the PLL is off. So it's as good as just disconnecting the chip from the power supply. Yes, absolutely. Core clock and PLL, what is the difference? PLL you can think as the clock source. It generates the clock. Core clock is the clock which you get after you take the clock from the clock source, you pass it through your clock distribution network. And then that is the clock which comes to each other flip-flops. That is your core clock. So frequency of both will be the same. Or sometimes it could be, as you said, in the DFM, in the last example, the clock, you could have a PLL and then you could have some dividers with programmable dividers and so on. So you could have some.
With the 600 megahertz wave, core clock and PLL frequency differ?
That I don't know. That's a good question. I don't know whether they have changed the PLL to 600 megahertz or because it's not doesn't seem like obvious divide ratio, right? Yeah. Pardon? Where is the PLL based on? Oh, base clock. Okay. The PLL needs a clock reference. It will usually be some crystal which will be outside the chip, and there will be a little oscillator circuit which will resonate with the crystal. Now, see, in the system something has to be alive. Okay, so so there will be some very, very low power clock which could be running, very low frequency clock which could be running in the background. So you saw that you have these voltages which are changed from 1 volt to 0.75, and even in the last few classes we saw how you could use voltage, reduce the voltage if you are reducing power. But the chip is in part of a system. That means there are other chips to which it has to talk to. Maybe those chips don't have this voltage reduction capability. For example, the IOs out here, right? The outside chips, maybe you have a memory chip, you have a flash chip, they have fixed voltages. So that means this interface has to maintain the voltage. So when we change the voltages, we usually change the voltages of things inside the chip, not at the periphery. Because at the periphery, we still have to talk to outside chips which are expecting certain standard voltages, 3.3 volts, maybe 5 volts, right? So what that means is that, and even inside the chip, there could be regions which have different voltages. Maybe you have done this optimization where you have multiple power supplies, you have many cores, each core running at a slightly different voltage and so on. So you need to be able to exchange signals between these two different voltage domains. there is a similar analogous problem of timing. Each entity here could be running off a slightly different clock. So that is something we'll discuss when we discuss about clocking, how you would exchange information across different clock domains. Okay, so here we will just see how we will exchange information across different voltage domain. So when we go from high voltage domain to low voltage domain, it is actually very simple. It's just a simple inverter. Say on this side N1 and on the left is a high voltage domain. Okay, that means all the gates are running out of the VDD-H supply. From there I want to send a signal to VDD-L. Well, I don't do anything different. I just have I just connect the output of VDD-H to input of VDD-L gate, and everything works fine. There is no issue. Except of course you'll have, if you see out here, when N1 is high, the NMOS gate overdrives VDD-H minus VT. Whereas when N1 is low, the gate source voltage is only VDD-L for the PMOS. So with this, what happens is the PMOS is, at least for the first gate here, have lesser drive than the NMOS. So you have to compensate for it if you are concerned about delay by making sure the PMOS size is sized accordingly to account for that difference in voltage. But other than that, there is really no issue here. Except when VDH value is so large that it can damage it's above the recommended voltage for this. That can happen from the IO. From the IOs are 3.3 volts, but internal transistors are just 1 volt. So when you want to send get signal from outside to inside, what do you do? So then this kind of thing might not just be sufficient, but how to deal with that, that is kind of beyond the scope right now of this class, but that is something you have to watch out for. Okay, typically what happens is the IOs, the transistors have thicker gate oxide, so they can withstand higher voltages. The core transistors have thinner gate oxide, so you have to basically make sure you don't put too high a voltage. So maybe that gives you a clue as to how to handle that. Perhaps you have to ensure maybe some series connection of devices so that effectively across each device you don't get such a high voltage and so on. But that is kind of beyond the scope of this course. We will not get into that. Low voltage to high voltage, if I just do the same thing, it is not a good idea. Why is that? Right, because what happens is that this N2 node which is driving this will not go all the way to VDD-H, it will only go to VDD-L. That means this PMOS is never fully off. So it will always be leaking and it may not even work properly because it's like a pseudo NMOS, and so it's not a good idea to do it this way. So you need to do something different, and this is what is done. The low to high conversion process is a kind of a tougher thing, and this is a very simple circuit which does it. Okay, let us see how this circuit works. So the problem was basically in this, that the N2 was never really going all the way up to disconnect the PMOS. So that is basically being fixed like this, where the low signal is never connected directly to the PMOS. Okay, the PMOS is driven by this kind of a cross coupling. Okay, the input signal A is fed to N1, but then you also have this additional transistor N2 which is fed with the complement of the signal. So now how does this work? Let us say X is 0 to begin with and Y is 1. Okay, so X is 0 means P2 is on, so Y is 1. And X is 0, that's because A is 1, X is 0, and N2 is off. So this is just like an inverter. N2 is off, P2 is on, and Y is high, so P1 is also off. So everyone is happy. N1 is on, P1 is off, so X is 0. N2 is off, P2 is on, Y is on. Okay, so there is no extra leakage or static participation or something. Now let us say A goes from 0 to 1. 1 means VDD-L. No, I'm sorry, A was already at VDD-L because N1 is on. A goes from VDD-L to 0, shutting N1 off. But P1 is also off right now, so nothing really happens. But when A goes from VDD-L to 0, this is just an inverter. So this goes high and N2 turns on. When N2 turns on, what happens is Y, of course, for that instant, both P2 and N2 both are on. But this is where you have to size things properly such that N2 will win, N2 will dominate and start driving Y down. As it starts pulling Y down, P1 starts turning on. And as P1 starts turning on, it will start charging X up and disconnecting and turning off P2, which will help Y to come down even faster because Y was being held up. N2 is fighting against P2, but P2 is slowly shutting off. So it's a positive feedback. It just helps to, everything is going the same direction and Y comes all the way to ground. P1 turns on fully, X goes all the way to VDD-H because P1, and then P2 is fully off because X is at VDD-H, source is at VDD-H. So once the whole transition finishes, again you don't have any quiescent current other than the usual subthreshold leakage current. So this is basically how the simple level converter works, and there are variations on this and so on, but this is the basic idea, right, of how the level converter works. So So when we reduce the supply voltage, right, we had kind of said that energy starts, power starts coming down because energy and power both are function of VDD. But if you look at energy per operation, okay, it turns out that having a very low supply voltage is not good. In fact, energy goes up. Energy per operation will start going up. Why? Because it takes longer and longer to finish the operation. Because as you reduce the voltage and you start hitting the subthreshold region, the currents become so low that takes longer and longer to do one job. And during the time you are doing that single cycle, single operation, you are leaking all throughout. Leakage power is there, I times V. Of course, V is very small, I is also reduced, but still it is there. So I times V times T is the energy. T is the time for that operation. And the time for that operation starts going up, because things have become slow. So what that says is that the energy per operation, which consists of two components, leakage energy per operation, dynamic energy per operation, the sum of the two, initially it starts dropping because it's dominated by the dynamic energy. Dynamic energy per operation reduces, continuously it will reduce all the way down. That is not an issue, but the leakage energy per operation will start increasing because it's taking longer and longer to finish one operation. And so it turns out that there is if you are just interested in minimizing the total energy per operation, there is an optimum point, optimum supply voltage. Why is this interesting? Because a lot of battery operated. A battery has a finite amount of energy, which means if you want to make the battery last longer or want to do more number of operations using that same charge, you have to reduce the energy per operation. That is where it becomes interesting. That if I want to do more work, more computing in this battery based applications, it's interesting to know what is the optimum setting which will minimize the energy per operation. So there is a notion of an optimum voltage. You don't want to make the voltage very low. It turns out this voltage is at near the subthreshold, few hundreds of millivolts. We know that VDD min is very low, right? Theoretically we saw that it is about 50 millivolts. But that is not the right place to be operating. Even though things could work there, it's not right from the point of view of optimum energy. You want to be away from it. How far away from it should you be? It really depends on some details of the technology and so on. Maybe a few hundred millivolts. Okay, so that is the concept of minimum energy point. And you see this minimum energy point really, it's kind of comes because of a balance between, dynamic and static energy, right? Something causes, say, the leakage to go up. Say temperature goes up, threshold comes down, leakage goes up. That means leakage energy cost has gone up. Then what I need to do is my optimum will shift a little bit to the right. I want to use a slightly larger voltage to do my job faster and finish it off because it's too leaky, right? Similarly, when the dynamic goes up, then I want to reduce the voltage I use. Okay, so that means that my optimum shifts to the left because I want to reduce the penalty of dynamic. So this is kind of so the optimum energy point, minimum energy point, basically depends on the balance between leakage and the dynamic energy. And this is also, remember, we had discussed a few lectures back about power dissipation also. If I have a, when I have what is the right balance between leakage power and dynamic power? If my leakage power is very small, it means my thresholds are very large, and for that same speed, if I could reduce my threshold, I could reduce my supply and reduce my dynamic. So where should I be sitting? You see, the same argument is coming out here. The leakage, there has to be a balance between leakage and dynamic for you to have the optimum power or optimum energy. Now the interesting question is, how do you find this optimum VDD? You want to find this optimum VDD automatically in your circuit. Your circuit should hunt for it and get to that point and always be operating at that point. So that is something which is interesting question, and some people have worked on it, but it's kind of beyond again the scope of this particular course. So I'll just point that out, and you can read some papers on that. But what is interesting also is that corresponding to that, this is not surprising that there is a notion of an optimum speed at which you should do things, which will minimize the energy per operation. What I've done is, in the same graph, now I plotted the frequency versus voltage. This curve is familiar, right? Higher frequencies at higher voltages, lower frequency at lower voltage, and I just superimposed the same energy versus voltage curve. And there is, at the point at which I minimize my energy, I use that voltage, energy per op, and whatever frequency I get, that is the right frequency for me to run. Okay, so what this says is that, suppose you had an application which had a certain throughput requirement, and you say this is the frequency, target frequency. If that target frequency is less than this optimum frequency, what it means is you should run at the optimum frequency, which is faster, and then shut yourself off. Okay, it is like most of you have motorbikes or cars and so on now, so you don't want to go too slow. It's not good. You'll just be burning too much petrol. Just take the limiting case where you are just standing in one place and idling. You have not made any forward progress, but you are consuming energy. That is totally waste, right? So there is a certain optimum speed at which you should be running, so that you really minimize the amount of energy you consume, amount of petrol you consume. It's the same thing which applies here. There is an optimum speed at which you should do the computing, right? Of course, if the throughput requirement is higher, of course you have to run it at that. You can't. If the F target is higher than F op, you have to run it at F target. Otherwise, you will not finish the job. But F target is less than F op. It's better to run it faster than what is required and shut yourself off. So this voltage at which you run, at which the energy becomes minimum, turns out to be very low voltage, about 200, 300 millivolts. So it's in the sub-threshold region. So is this kind of interesting? Okay, I mean, it's kind of interesting from an academic perspective, but practically is it interesting? Because that F opt speed, what is that F opt? It turned out that F opt was in the kilohertz range a few years back. But now F opt is in the megahertz range. So it's kind of becoming interesting. Why is that? Because if you look at technology scaling, right, delay is CV by I, right? C is what? Cox WL, if we ignore the wire out here, Cox WL VDD, and current is K Cox W by L times E VDD by NVD, because we are in the subthreshold region. So when you do this, simplify everything, delay is proportional to, in the subthreshold, L square times VDD. Suppose we said VDD, it's kind of a low voltage, we have some fixed VDD. As you look at L square, that means as my technology, every year and a half, L is reducing by 0.7. Every 2 years, say L is reducing by 0.7. That means the delay is reducing by 0.5. Half. You just wait 2 years, then you do your chip design, it will be twice as fast, the same gates. And also I can pack twice the number of gates. So maybe you have 2 cores. Instead of 1 core, I double the number of cores. So if you have applications which can be parallelized, I can have twice the number of cores at half the delay. That means my throughput is increasing by a factor of 4 every new generation. So what this is saying is that with technology scaling, even the f-opt itself is scaling or increasing at the rate of 4x. So that is why now f-opt we are in the regime of few megahertz throughput, which makes it very interesting that a lot of the designs will try to operate at this point of minimum energy. So it kind of makes it a very interesting research challenge. One of the challenges is when you design the chip, making it run at this only at this particular set of voltages itself is a very risky proposition. Maybe we are still not ready yet. So you want to design chips which will run at both high voltage as well as low voltages. You should be able to span these large voltage ranges. So there are some challenges there, and it's just again going into that in detail will be difficult in this course, but just something I'm pointing out. It's an interesting topic for research. So we have been talking of minimum energy, right? So what is the minimum energy? What is the connection between energy and computation? Computation is a mathematical concept. So what is the connection between physics and maths? We use maths to describe physics, but is there, why are these two linked up together like this? And this was looked at by this guy Ralph Landau from IBM, where he basically said, he proved that you really don't need any energy to do computation. You can do it with zero energy. Okay, provided information is not destroyed, and we'll see what that means. You have to do things in a reversible way. So, in fact, that was one of the motivations for looking at this very low voltages and so on. But even the voltage of whatever 48 millivolts is coming from the limitations of this particular CMOS type technologies, right? What this statement is saying is that there is really no limitation. I should be able to do computation with zero energy. And to do that, we need to do things very slowly in a reversible way. In thermodynamics, when you have adiabatic changes, right, when the state of the system changes from one to another, if it happens in a very slow reversible way, right, you don't have net loss of energy. That is basically what you have to do out here. Things have to be done in a reversible way, in a slow enough way. So, but our typical circuits, they're not reversible. You take an AND gate, X, Y, F, 0, 0, 0, etc., etc. From F, if someone were just to give you F, you cannot infer what the input was. So you have to make it reversible. How do you make it reversible? Well, what you do is with X, one of the inputs, you send it to the output. Now, from the output, I can get back the input. Okay, so this is something which was looked at 60s, 70s and so on, where a lot of work went to design reversible versions of gates and so on, so you can make everything out of reversible logic gates towards the quest for zero energy computation. That means you do computation without consuming any energy. Okay, now of course that whenever we do computation in our CMOS type circuits, we are always charging discharging capacitors. So can we break that barrier? Because we know when we charge a capacitor, we said last time half CV square is lost. But it turns out that you can charge capacitors without having to lose that, if the voltage source which is charging it is a ramp. Okay, say for example it is a ramp and it has a certain rise time of t, then it turns out that the energy loss to charge the capacitor is related to ratio of RC by T times CV square. So the T, you make it slower and slower and slower, you can end up charging the capacitor to full voltage V with asymptotically zero energy. Okay, so that is basically the concept of adiabatic changes comes in. You do things slowly. How do you make a ramp? Well, one way is with an inductor. You put an inductor, and now you have what is called resonant charging. And in this charging, if you recall from your basic EE or physics, high school physics, when you close this, what you have is you have an LC tank. If you just close the switch, LC tank, you will have a sinusoidal wave. In an ideal setting, it will just oscillate forever and no energy is lost. Okay, energy keeps settling between inductor energy and capacitor energy. Of course, you'll have some losses which gets replenished by the battery, but losses are much less and related to the Q of the circuit, 1 by Q CV square. Q is large, very high quality, that means very low resistances, you'll have very low loss. So people basically said, okay, let me put reversible circuit. So I need two things. I need to have reversible circuit blocks as well as the ability to charge and discharge in a way where I don't lose energy. So they put two things together. I'm just schematically showing some gates with pull up, pull down, etc. But then what you have to do is you have to, for example, you charge it up and then you discharge it again. You take the energy back. Similarly, but you might have to have multiple phases and so on. So a lot of research work was done to develop these kinds of approaches where the power supply now to the chip itself is a clock, resonant clock. It goes up, comes down, goes up, comes down. You will have multiple phases and so on. Again, this I'm not going into too much detail here, just to give you a flavor for what kinds of things people are looking at. The thing is that approach has never become mainstream. Okay, even though there are a few papers every once in a while. And one of the reasons is, of course, you need inductors. So inductors are big. Okay. Second is that really energy saving is related to how slow you go. But we can go slow by also reducing the supply voltage. So that seems to be a better and lower overhead way to reduce energy. If I'm going to trade off speed and energy, I might as well do it by reducing the voltage rather than putting a lot of inductors and complicating my life. But this concept is still kind of very useful in specific scenarios. For example, clock networks, we'll just see an example. Specific places where, I can't reduce the voltage. I need to drive an LCD panel. There is a certain voltage I need to use. So why not do it in a resonant charging way as opposed to a non-resonant charging? So there are places like that where you can think of applying this kind of idea of resonant charging. Another very interesting spin-off of this, of course, I wouldn't say spin-off, but related to this, is this quantum computing, which is something which is maybe still in a very infant stage. In quantum computing, the basic devices are described by quantum mechanical equations, and in quantum mechanics, all transitions are reversible. State transitions are reversible. That means if you want to do logic with quantum computing, you also have to have reversible gates. So again, these gates have become very useful from that perspective. Okay, so maybe another 10-15 years, this might be something we might have to change the course we are teaching to do more quantum stuff. But for now, you don't have to worry about it for your exam. Okay, so the resonant charging idea is basically what you have is, say this is your clock distribution network. Okay, that is represented by a single clock capacitor, single capacitor. That capacitor is connected to a tank capacitor through an inductor. The idea is that because a clock is very specific, it's a periodic signal. You let this LC tank give you the periodic oscillation. Because an LC tank, very nicely, it kind of gives oscillation with very low loss, depending on the Q of the thing. And whatever losses are there, you compensate by this gate out here. Every period, you ping it, so that you restore the energy. But the idea is that the amount of energy now you have to draw from the supply is less, because this tank is, you're kind of just sloshing back and forth the energy because it's an oscillator. So this is something which it might seem very crazy, but it has been demonstrated in this chip from AMD. It is a 2-core x86-64 chip, and what it has is, in its clock distribution network, periodically they have all these LC tanks, and the L is implemented by a coil on the chip. So you have a number of these, and so you see this paper appeared only this year, January 2013, so it's a very recent paper. And the inductor itself is implemented using metal 11. So they have all the way to metal 11, which has very thick metals. So you have very low resistance in the metal, because resistance in the inductor is degrades the Q of the inductor, right? So use a top level metal to make this inductor structure. You just make it like this, and then it goes in. Here is the via, it goes down to the lower level and so on. And with that, they were able to reduce 25% power in the clock network compared to not using it, which translated to about 4.5% saving when some actual work was being done by the processor, and idle 10% reduction in idle power. So it's kind of interesting, like, what different ideas people are trying out in the quest for reducing power. So again, you can look at this if you're interested to explore further. You can read this paper from Sathe and company in IEEE JSSC. JSSC is Journal for Solid State Circuits. A lot of the circuits related work gets published in this journal. Okay.